This is problem 3 of practice exam 8 in chapter 1 from the book Problem Solving with Differential and Integral Calculus. It involves a pendulum swinging back and forth. Humans used pendulum clocks for a long time. The problem with the pendulum clock was if it was cold out, the length of the pendulum changed and it swung faster back and forth. And if it was hot out, the length of the pendulum increased and the time it took to go back and forth was slower. So it's inaccurate. Not by much, but every swing it's inaccurate. So after a while, it'll be pretty far off. So here's a graph. If you have a pendulum that's 1 meter long, it's going to take very close to 2 seconds to go back and forth. So 1 second to go back. So from one side to the other, it's very close to 1 second. And that's what a grandfather clock is. So draw a good tangent line to get the relationship between the change in the period, delta t, the rise, and delta L is the run, around 1 meter. So let's first identify the point. It's right there. Next, we draw a good tangent line. And then the rise looks like it goes from 1 second to 2.5 seconds, which is 1.5 seconds. And the run is the whole range from 0 to 1.5. It's 1.5 meters. The slope looks like 1 second per meter. So if we have any delta L that's small, we can calculate the delta T as long as it's close to a length of 1 meter. We can't use this equation over here because the slope is not 1 second per meter. We can use that equation right in here. We're estimating it with the tangent line. It's not exact. We didn't use the difference equation. So now we're going to estimate the difference in the period, delta T, when the length changes from 1 to 1.01 meters, which is 1 centimeter longer. So there's our estimate from the tangent line. Delta L is 1 centimeter, which is 0.01 meters. So delta T is 100th of a second. So the period of a pendulum that is 1.01 meters is 100th of a second longer than the period of a pendulum that has a length of 1 meter. On to part C. We have to get the difference equation from the normal equation. There's a square root in there, and square roots make things hard, so all we do is square both sides. So square both sides, we get t squared 4 pi squared L over g. Now we can see how L changes with t. We just plug in a t plus delta t for the time and L plus delta L for the length. Everything else is constant. So we multiply everything out. We subtract t squared from both sides. T squared is 4 pi squared Lg right here. T squared 4 pi squared Lg. And we get that for the difference equation. The linear part, we could ignore the delta t squared. We get that. If we want to get the slope, we could ignore the curvy part, which is the nonlinear part. So let's use the normal equation up here to eliminate t. We're going to plug in 2 pi squared L over g for t in this equation. We only want the delta t. So we're going to substitute 2 pi squared L over g for t. That's given. That's the expression. That's what's being plotted. So now we don't have any t's anymore. We just have l's, which is what we want. We want l's, delta l's, and delta t's. So we solve this equation for delta t, and we get this. Now we can substitute 1 meter for L. L's right here, and delta L of 1 centimeter. And we should get very close to 0.01. And we do. 0.01. I plugged in for g, acceleration due to gravity, 9.81 meter per second squared. This was also an estimate because we threw out the nonlinear terms. It's not exact, but we're not going that far.